Hey, this is the last lecture of the course, so thanks for being here, lasting until the end. Today it will be about connecting what we have learned so far in conformal field theory to the sphere packing problem, and it will build on the previous lecture where I explained some theorems in conformal field theory. But if you weren't here, don't worry, because I'm going to remind you what a theorem is. To solve the sphere packing problem in 8 and 24 dimensions. So this is the theorem. Suppose that you have some set of non-negative integers, discrete set of non-negative integers, delta I, infinite increasing or non-decreasing set, starting at 0. And suppose that with each delta I in this spectrum, so we will call this the spectrum. So for each point in the spectrum, there is some positive number C5i squared, which is this OP coefficient squared, such that the first one corresponding to identity is just 1. It's just normalization, and such that the crossing equation is satisfied. So this is the conformal bootstrap or crossing equation. It tells you that when you sum over the whole spectrum with these coefficients, so it's linear in these coefficients squared, the conformal block minus the cross-channel conformal block, then this is equal to 0. And this should be true. This should be true for any value of the cross ratio between 0 and 1. So it's an infinite set of equations labeled by this continuous parameter z for infinite set of unknowns, which is the spectrum and these c's.
Set of data. Are you sure they always exist?
So that's exactly the point. No, it doesn't always exist. In fact, that's what the theorem says. The theorem says, a necessary condition for the set of C's to exist is this one: that the first delta 1 better not be too large. If delta 1 is greater than 2 delta phi plus 1, so if delta phi is a parameter, or you fix delta phi once and for all in this theorem, it appears only here. And so what we proved last time, at least, well, we sketched the proof that delta 1 has to be at most 2 delta phi plus 1. And otherwise, you cannot find a set of positive C's which satisfy this linear equation.
Delta phi is the discrete dimension of the externality.
Delta phi is the physical meaning of delta phi is the dimension of the external.
The all internal operator scalars?
It's 1D, there is no spin. I mean, it's just true for CFDs in n dimension because you can always take your first restriction into a line. But once restricted to a line, you forget about spin. And the bound is actually saturated by a 1D theory, which is a generalized free fermion, where the spectrum is of this form. So it's 2 delta phi plus all positive odd integers, 2i plus 2i minus 1. I start from 1. And there is an explicit formula for the C's in terms of some Pocanus symbols, but don't worry about the formula. It's positive for any. Okay, so that's the theorem. And the proof, maybe I'll put the proof at the top. So the proof uses this notion of an analytic extremal functional. So analytic because it's an analytic proof, extremal because it proves extremality of some specific solution to this crossing equation. So the analytic extremal functional is denoted omega. It depends on delta phi because we have a new theorem for every value delta phi, and omega changes the function delta phi. And then we introduce this function omega of delta, which is the action of this linear functional on what is in the square bracket here. Okay, so it's the difference between the so-called S-channel conformal block minus the D-channel conformal block. And then, in order to prove the theorem, we need to construct omega such that this omega of delta has the following structure. So it needs to be non-negative. Oh, there's a pointer here. It needs to be non-negative from the gap that you're trying to prove. So that's this point. So it needs to be non-negative for all delta greater than that. But because it's saturated by the free fermion, it actually has to vanish on the spectrum of the free fermion. And this is a very similar phenomenon what we saw in the first lecture for quantum mechanics, and the second lecture for the ODEs, where we got this nice limit cycle where the extremal function needed to vanish. So here the analog of the limit cycle is the set of points where the extremal function needs to vanish onto delta phi plus integers. So then just these conditions, there is a simple 0 at 2 delta phi plus 1, there are double zeros at 2 delta phi plus odd integers. And I explained to you how to construct this omega as a kind of abstract linear function acting on functions of z as a kind of sum of two contour integrals against two kernels, a and b. And now the a and b's are not arbitrary, but they are chosen such that omega of delta looks like that. The way this works is that there is a contour deformation which brings this contour integral to the. So what this is the action on a general function, and this is the action on whatever f is in the square bracket in the theorem. And the claim is that if a and b are chosen well, the unique choice, then you can make a contour deformation which expresses this action as follows. So there is some cos squared delta minus delta phi, which is responsible for the oscillatory behavior of double zeros. And we can check that this exactly vanishes when delta minus delta phi is an odd integer. Times, maybe I should put this down again.
Okay. You have this formula. You have delta phi of f, of course, times the a term. But no delta phi.
Yeah, so A and B will depend on delta phi. This is just in general.
Okay.
Maybe I can put it.
Okay.
Yeah. So here's the A for delta phi 1/2. This is it for 3/2. Or otherwise delta phi is hypergeometric. This is just some sort of general answer which you need to choose to. So this integral is positive, but it diverges when delta is less than 2 delta phi plus 1, which softens the double zero of the prefactor into a simple here. The integral has a pole, simple pole. And then here you have to, define this boundary continuation or use this original prescription, which is convergent everywhere. And okay, A and B are subject to some functional equations, which I didn't reproduce today, but they were shown in the last lecture, which guarantee that this is that this operation works. And these functional equations have a unique solution for delta phi equal to 1/2. The solution is this one. I'm not showing B, but it's also unique with X. For delta phi equal to 3/2, there's also a unique solution, which is this one. It's always some rational function of z. Same for B, it's also a rational function of z. For otherwise delta phi, the solution is more complicated, so it's not a rational function. There are some logarithms, and it's some hypergeometric function. But at least for these two very special values of delta phi, the solution is very simple. So that's the summary of the last lecture. And today we are going to use this to solve the split packing problem in 8 and 24 dimensions, where, well, one thing I can already say is that the dimension of the sphere packing is 16 times delta phi. So there's going to be some general mapping between the problem that I was describing before and the sphere packing problem. And under this mapping, the parameter of sphere packing is the dimension related to our parameter, which is delta phi, using this formula. So when delta phi is 1/2, you get equal to 8. When delta phi is equal to 3/2, you get equal to I4. And this proof, or this theorem, when applied to sphere packing, reproduces the solution of a sphere packing problem due to Vyazovska and collaborators in these two dimensions. There's the same method discovered kind of independently in two different steps. To explain this, mapping is the goal of the lecture. I'm afraid to save time, I'm going to erase this beautiful piece of art.
Could be any way to carve it. Or
Yes.
so,
Exactly. Are there any more questions about this recap? No. But basically, the whole point is to find some.
If you go to higher than 3/2, or delta phi has.
Well, then this thing, the CFT functional still gives a valid bound on sphere packing, but it's not a particularly strong bound. It's no longer saturated. It's not sharp. For CFT, it's sharp. So it's sharp for any delta phi because the free fermion is saturated for any delta phi. But for sphere packing, the problem is slightly different. So it's not.
got it.
The
function omega that you have there on the bottom on this board, which took the form of a cosine times an integral between 0 and 1. Looks like there's some similarity with Lorentzian inversion formula. Would you comment about this? Or?
Yeah, it's well, I don't want to comment too much because maybe not everybody knows what Lorentz inversion formula, but yeah, it's these analytic functionals you can they indeed have the double discontinuity in them. So if you know what the d-disk is, then in some sense this analytic functional reconstructs the d-disk. That's all I can say. I can point you to some reference where the relation is made more explicit. Alright, here I think. We have quite a lot of material to cover. What is the sphere backing? It's a sphere backing. In d Euclidean dimensions. Well, sphere backing is just a configuration of non-overlapping spheres in d dimensions of equal radii. So these spheres are allowed to touch with their boundaries, but not with their interiors. And the question is, what is the maximal density? Which I'm going to denote rho for density, star for maximal of d in d dimensions over all sphere backing. So by density, I mean the proportion of space that's an average taken up by the spheres. You can define rigorously if you want. You pick some configuration of sphere, which by the way doesn't have to be regular at all. You just sphere backing is specified by the location of the centers of the spheres. All of the centers of the spheres need to be at a distance from each other, which is at least twice the radius of each sphere. So that's the only constraint. And then you can define its density by taking some large sphere, which insert some large radius r, computing the proportion inside taken up by the spheres compared to total volume of the sphere, and as they take the radius to infinity, the limit, I guess the lim sup, limit, I always get these two wrong, is well defined. So that's how you define the density completely rigorously, but the intuitive picture is clear, right? And in general, it's a very hard problem to find the optimal sphere backing in general dimension, but it's actually solved in several dimensions, namely 1, 2, 3, 8, and 24. So in one dimension, it's quite easy. So one dimension is just a line, and you can cover the line by one-dimensional spheres with no spaces in between them. Right? So if these are the centers of the spheres, just do it like that. So rho of 1 is 1. Perfect covering. Okay, that's not the end of the lecture yet. You can go to higher dimensions. In 2D, well, you want to take a guess? Some of you probably know what the most of you know. Okay, good. You basically you repeat this one. You put this next to each other, and then you just keep stacking them. You repeat this one-dimensional configuration, but slightly shift it so that now they lie in the valleys in between. And this defines the hexagonal lattice. The unit cell is the union of two equilateral triangles. And so it's called, I guess, the hexagonal backing. You can check for yourself. Oh. Okay, and you can check for yourself that the density is this one. So pi over square root of 12.
This is optimal.
Well, it's very easy to see intuitively. I think there's nothing you can do better. But actually, the first proof, which is considered to be completely rigorous, only appeared in 1940. So this is actually due to he was building on work of these 1940. Okay, but so in general, the spheres in a sphere packing don't have to form a lattice, but it's maybe let me just first say what is a lattice before I keep going to higher dimensions. So a lattice is a discrete subgroup of RD of full rank, so meaning that it's isomorphic to ZD. So lattice packing is just when all the spheres, all the cylinders form a lattice. And more generally, you can talk about periodic packings. Packing is periodic if the set of sphere centers has a symmetry, which is a lattice, and there are only, and then as a consequence, there are only finite element orbits under this symmetry. So you can write, there is some lattice lambda, and there is some finite set of basic vectors, x1 to xn in Rd, such that the set of sphere centers is the set xi plus y, where I is one of these vectors and y is in the lattice. So in 2 dimensions, you could have this hexagonal packing if you want, which is lattice packing, but then you could add say another point somewhere here and periodically shift it. So this would be an example. I'm drawing this very well. So you could add another vector here and try to fit spheres. You would have the 2 vectors in this case would be say x0 would be the origin and x1 this would be x1. This is basically what I mean by periodic. Yeah. It's I don't know how much I should explain, but I guess I'm over explaining sometimes.
You talk about optimal packing. What about opposite from least optimal packing? Does that make sense?
Least optimal packing is when you don't put any spheres at all.
Oh, yes, exactly. But I meant for default too.
Yeah, we have very long, but I mean,
But there is a well-defined program that is, if you want to find a packing that is stable under compression, so if you do that yes, that is stable under compression, that is the less dense one. This is actually, it can, this is
Sorry, if you have the centers, can you reconstruct the radiuses?
is the radius is this minimal distance between centers divided by 2.
Minimum, okay. So I look, okay.
Yeah, so for a periodic packing, what's the density? There's a formula. The density is, well, the volume of the unit ball in d dimensions. So this is how I'm going to denote it. So radius 1 d times what I was just saying now. So this is the r star is the shortest distance between sphere centers over 2 because the spheres need to not touch to the power d. So this is the volume of the ball forming the sphere packing times n because there are n of them per unit cell and divided by the volume of the unit cell, which I'm going to denote. It's a simple formula, but it's good to write it down smoothly because I'm going to refer to it later on. Okay, so this is the density of a periodic packing of the periodicity lambda with n orbits under lambda, where r star is the shortest distance between points in that periodic configuration. Okay, and now this was just a last intermezzo. Well, let me quickly say what happens in D equal to 3 dimensions, which is kind of interesting, but somewhat tangential to what I'm trying to say today. There, well, the Kepler's conjecture was that the optimal packing you basically get by stacking layers of the two-dimensional packing on top of each other in the third direction. But now you have some choice. So let me just actually use this picture. Right, so you can either you can either use these points, or the complements. You cannot use both of them in the second layer, and then when you go to the third layer, you can either go back to you can either put it exactly the same as in the first layer, or you can use the other choice. So you basically have some alternating choice, and the packing is not unique. There is actually an uncountable infinite and inequivalent set of packings, but they all have the same density. There are two lattices which realize it. It's either the face-centered cubic or the three-dimensional hexagonal lattice, which correspond to alternating choices of these shifts. And they all have density, which is pi over 18, square root of 18. But I also encourage you to check.
It took a long time.
Indeed, yeah. So this was eventually the proof was given by Hales, who used basically used the proof by exhaustion with a heavy usage of computer assistance. It took, I think, like a decade to verify the proof eventually, but ultimately it was fully accepted, and it is now a theorem of Hales that this is the optimal sphere packing in 3 dimensions. Now, the story is also very interesting in very, very high dimensions, where there's a lower bound due to Minkowski, which is of the form 2 to the minus d. There are some improvements of it. Actually, this was improved slightly last year, but I'm not really going to talk about it. And then there's the upper bound. So this is at large d. Then there's the upper bound, which is about 2 to the minus 0.599 something. So this is some number. This is due to Kabatiansky-Levenstein, so I'm not going to write that to save time. So like 1978, and they're still exponentially far away. So we know extremely little about higher dimensional sphere density because these two bounds are exponentially far away from each other, and yeah, some people believe that the truth is basically Minkowski, at least when it comes to the exponent. Some people believe it's more like somewhere in the middle.
So it's density for any packing or only periodic packing?
Oh, any packing. Sorry, this is rho star of d. So what is the general?
Are you missing a D in the exponent, or?
Oh yeah. The general idea is that as you increase d, lattices perform worse and worse. So eventually, in very, very high dimension, it's kind of expected that the better packings are more disordered than lattice packings. And order in dimension 10 is the first case where the best known packing is not a lattice packing. It's a periodic packing where capital N is equal to 40. It's still periodic, the best one which is known in 10D, but it's certainly not a lattice packing. And
sorry, the inequalities are for all D or so for large D?
Definitely large D. And okay, I'm just there are probably some constants and some sub-exponential factors, but this is
Okay.
if you take a logarithm divided by D, then these are the optimal numbers, either +1 or +0.5.
Is it already excluded that as you go in other dimensions other than the ones you described? Like, why you cannot repeat the method that you described here, like overstacking the d-1 packing and then you shifting it?
Yeah, you can repeat it. You just don't get the best packing. Well, it's proven in sufficiently low dimensions that when you do this method, you get something, and then you can find something which is better, which doesn't use methods.
More spheres into the gaps. Dimension 4, you can start putting extra spheres into the gaps between the.
And the dimension 4 is the D4, which is conjectured to be optimal. Which I guess you can maybe get by filling in some gaps.
The statement that it's the same problem with the map with the problem of infinitely effective potential of charged particles. What I mean, if I give some infinite charge.
You can generalize the problem by looking at a configuration of points with some potential, and then this is a special case where the potential is like a what do they call it? Well, potential well. So you can generalize. Yeah, the problem has really many generalizations. This is one of them. There are many other ones. You can do it in hyperbolic space. You can do it on the sphere, where it's called the kissing number problem. Kind of how many spheres can touch each other. Yeah. So. Okay, so the problem is solved in 8 and 24 dimensions. Also, this type 1, 2, and 3. And that's work of Vyazovska, who first did it in 8 dimensions, and then about a week later, they wrote a paper with Henry Kohn, Abhinav Kumar, Steve Miller, and Kravchenko, plus Vyazovska, where they solved it for 24 dimensions using basically the same method that Vyazovska. And the theorem is that so the best packing is the E8 lattice. So the sphere centers form the E8 lattice in D equal 8, and the Leech lattice in D equal 4. So before I tell you what, sorry, 24. So before I tell you how to prove it, I first need to tell you a little bit about these lattices. So in particular, in 8 and 24 dimensions, the best packing is a lattice packing. And I was just convincing you that in general, in high dimensions, it shouldn't be lattice packing, but some of these two dimensions are very, very special, where there exist these very special, highly symmetric structures, which is the E lattice and the Leech lattice, that you can actually do it with a lattice. So what are these lattices? Let me first give some simple definitions. So the lattice lambda is called even lattice if all the vectors in the lattice have an even length squared. So 2 divides x squared. I'm going to, by x squared, I'm going to mean the norm squared. So the even, it's unimodular if the volume of the unit cell is 1. So that I'm going to denote it like that. So what's the unit cell? Well, you quotient RD by the lattice, so just an abelian subgroup of that, and this is the size of it in the usual Lebesgue measure. So if this is okay, this is 1, then it's called unimodular. The dual lattice of lambda is going to be denoted lambda star, and it's this thing is the set of all vectors in RD, which have an integer inner product with all the vectors in lambda. So all the y in RD such that for all x in lambda, the inner product of x with y is an integer. So that's the dual lattice. And what's the meaning of the lattice? If you want to decompose a periodic function per period first the lambda in RD, then these are going to be the momenta. The momenta that you're going to need for your Fourier series are going to lie in dual lattice. Okay, then there is a small small lemma, which is that the volume of the unit cell of the dual lattice. Does anybody know what is it in terms of the volume of the unit cell of the original lattice? You're paying attention. Inverse, yes. Okay. And you're not going to prove it. Another small lemma is that if lambda is even and also unimodular, then actually it's self-dual. Self-dual means that the dual is itself. This I'm going to prove quickly, just to show you some simple proof. So, well, note that for any, so let's assume it's even and unimodular. And for any x and y in the lattice, the inner product of x with y is equal to this. Okay, this is just the formula. But now each of these is a lattice vector, and their squares are even integers because lambda is even by assumption. So if you divide by 2, it's an integer. Okay. So it follows that the dual lattice is a subset of the lattice. So at every point in lambda is also in the dual lattice. But now if it's unimodular, the unit cell is 1, which means that it cannot be a proper. The index needs to be 1. I'm not going to write it. Actually, unimodular shows that the cardinality of the finite group, which is lambda star by lambda, is 1.
What is the even lattice?
Even lattice in 2D, it's the one. So you just take Z2, and you only keep those vectors where the two coordinates sum to an even integer. That's an even lattice, but it's not self-dual. There are no. Well, even self-dual lattice does not be the next one. Even self-dual lattice only exists in dimensions which are multiples of 8. But there are even lattices in n dimension. Let me just take Z2 and we scale it such that the basic element is a size. That's quite perfect. Okay, so that's the claim, which I'm going to come back to a bit later, that even self-dual lattices only exist in dimensions which are multiples of 8. You can most easily show this using some modular 4 technique, but I'm not. So the first time you ever meet a lattice which is both even and self-dual is in 8 dimensions, and there is only one of them, and it's the 8 lattice. So there's a unique even self-dual lattice in D equals 8, and is the E8 lattice. And you can construct it. Why is it called E8 lattice? Because it's a root system for Lie group Lie algebra E8. And here's how you can construct it. So E8 is the set of all points in Z to the 8. Okay, but this is a self-dual lattice, but it's not even because the 1 0 0 0 0 doesn't have an even length. So you need to do something extra. I'm just going to write it first. Okay, so what is it? So all of the points in the lattice are either in Z8 or Z8 shifted by vector that has 1/2 in all the components, but subject to the condition that all the coordinates, when you sum them, are even integer. And so this is a lattice where every vector has a norm which is an integer, and now this is a degree 2 sublattice where every vector has a norm which is an even integer. Another way of thinking about it is as follows. So you start with you kind of start with the essentially Z8 in some dimension. Just take Z8 or ZD, which is the most obvious lattice. So the square lattice in D dimensions, and color all the vertices with either black and white, such that no two neighbors have the same color. So when this is the same thing as saying when the sum of components is odd, it's white. When the sum of components is black, it's even. It's black. Now this defines some backing for you, where you put a sphere center at every white vertex, so where all the sum components is even. But this is not saturated. As you increase D, there are some bigger and bigger holes that appear. Where in 8 dimensions, you can add another sphere which is centered at this point, basically along the diagonal, halfway between the origin and the vector with all ones. Right? So in 8 dimensions is the first time where you can add a sphere of the same radius. What was I saying? So I was saying that imagine let's put the sphere centers at the origin, and then the neighbors of the origin are going to be all the vectors that have either that have 2 components not 0, each of them either plus or minus 1. So 1 1 0 0 0 plus or minus 1. So this is the root system of D8. This is the D8 lattice. But now I'm saying you can, in particular, there is a sphere centered at all ones. 1 2 3 4 5 6 7 8. But the gap between the origin and this vector is becoming larger and larger as we increase D. And 8 dimensions is the first time where the vector which is halfway in between can host a new sphere. So you can check the arithmetic. That's why 8 is kind of expected. Some more comments about the lattice. So a useful quantity is the theta function. So in general, you can define the theta function of a lattice. So it's some function in the upper half plane. So it's in the upper half plane. It's denoted as h, and it's defined as the sum of the lattice vectors of the IPhT x squared. Now for the E8 lattice, the theta function is just the Eisenstein space of index 4. And this one has a point square position, so it starts with 1. 1 is just the single vector of length 0. And then there are 240 vectors of length 2, norms for q. Okay, this q, what is the q? Q is e to the 2 pi I tau. So the powers of q just count the power of the Q is the norm squared divided by 2. These are the lattice vectors of length 2. There are 240 of them. You can, let's just count it from here, but what are the vectors of length 2? Well, it's either you have 2 plus or minus 1s and all 0. So that there are 8 choose 2. There are 8 choose 2 ways to choose which are 1s. Then you need to choose which plus or minus 1 twice, because there's 2, 1 plus or minus 1, so that's times 4. And then you have all of the vectors in here. So they are, 1/2, basically all 1/2, which can be either plus or each of them can be either plus or minus 1/2, but subject to this condition, which means that you need to have an even number of minuses. So that's 2 to the 7, because there's 2 to the 8 choices, but only half of them have an even number of minuses. That's 2 to the 7, and that's 2. But this existence series gives you a whole formula for how many there are. Now the Leech lattice. The Leech lattice is significantly more mysterious than the Leech lattice, but it's also unique in a sense. It is the unique even value or even unimodular. We already know their equivalent. In 24 dimensions, such that there are no vectors of length squared 2. The shortest non-zero lattice vector has x squared equal to 4. That there do not exist any acts in Leech with x squared equal to 2. So there are 24. This is kind of a funny numeric coincidence. In 24 dimensions, there are 24 non-equivalent even subdual lattices. They're called Niemeyer lattices, and only one of them has this property. So most of them have vectors with norm squared 2, as does the E8 lattice. The E8 lattice has 240 of them, but the Leech lattice doesn't have any of them, and is the unique one of this property. And correspondingly, you can write down the lattice theta function, which is now related to the modular change invariant. I like to write it in the following way: Dedekind eta times the J invariant, and don't worry if you don't know what exactly these things are, but they are modular forms. But if you actually look at the counting of vectors, well, there is the 0 vector, and then there are no vectors of length squared 4. In other words, length 2. And there is a rather large number of vectors of length squared 4. Oh, sorry, what would I? There are no vectors of length squared 2, but there are many vectors of length squared 4. And there are precisely 1, 9, 6, 5, 6, 0 of them. So, well, if you have some software, you can decompose this modular form to higher pairs of Q and see how many there are for higher lengths. Yeah, that's the number of. It's the number of shortest lattice vectors. So that's the number of spheres that touch any other sphere. So before the break, so these are 2 lattices, and each of them defines some packing, right? Where the radii of the sphere would be 1. So I guess the distance between the 0 and the shortest lattice vector is is 2 for the E8 lattice. So this the length of the shortest lattice vector for the E8 lattice is square root of 2, and for the least lattice it's 2. The volume of the unit cell is 1. So the sphere radii would be in this case 1 over square root of 2, and in this case 1. From this you can compute the density corresponding packing. The claim is that there is no packing in 8 and 24 dimensions, which is better than this packing when it comes to density. So how do you prove it? How did Vyasaska and friends prove it? Well, what they did is they proved a universal upper bound on the density of any sphere packing in any dimension, and then they showed that this upper bound is saturated by that's the proof strategy. The strategy. It's sort of beginning to sound similar to the in Boostrap. We had some universal upper bound on a slightly different quantity, which was the spectral gap for the CFT, which happened to be saturated by something that we knew with rather regular properties, which was the generalized free fermion. So the strategy through a universal upper bound for some general principles on this density, rho star of D for any packing, principle for any D, and show that it's saturated by E8 and leach in the two cases. And the proof of this upper bound is essentially identical to the proof that we had before. Or this is very similar to the proof from CFT, from 1D CFT. On the CFT. So I'm just going to give some kind of like sketch. Is that we had a proof of the statement that delta 1 is upper bounded by 2 delta phi plus 1. And under the mapping, the spectrum of this delta 1, delta 2, and so on becomes the spectrum of the length squared of lattice vectors. There's some kind of, we'll explain in the second half of the lecture, there's some correspondence between the set of deltas in CFT and the set of R squared for the corresponding lattice on the sphere packing side. And there's going to be a relation that I already said before, which is that delta phi is d over 16. But you can already see that to maximizing the density of the packing is like maximizing the length of the shortest lattice vector. The density is basically the volume of the ball of the radius divided by the volume of the unit cell. So if you normalize the volume of the unit cell to be 1, you're trying to find a lattice that has as large of a possible, whose shortest lattice vector is as large as possible. So it's like maximizing the lowest delta 1. So it's already beginning to sound very similar. And in fact, if you just plug in, if you look at this bound naively, you got that. So R1 squared, which is delta 1. So that should be upper bounded by 2 delta phi plus 1, which under this change of variables, which I'll explain everything in detail. This is just, if you just plug in this d over 16, then you get d over 8 plus 1. And that's exactly, so when d is equal to 8, that's exactly 2. Equal 8. 4 for d equals 24. So that's exactly what we want. We want to show that for any, more or less, that for any lattice, R1 squared needs to be at most 2, or more precisely for any subdual lattice. R1 squared needs to be at most 2 in 8 dimensions and at most 4 in 24 dimensions, which is what this naive mapping to the CFT problem would give you on the nose. The details are more involved because we want to prove an upper bound not just on lattices, but on all packings. That's one complication. which Colin Halke is brilliant and dealt with. But that's basically the only complication. Once you remove that, then.
But if you take okay, you said that for equal 8 and 24, it's true, it's optimal package.
Yeah.
But the last point, saying if you take the arbitrary, it's not going to be a
So this upper bound from CFD, if you go through details, applies below 8 and above 24, but it's not optimal. But it becomes optimal in those if you look into the details. The two-dimensional case is very interesting. Let me say a little bit later. Okay. Yeah. So the two main things that remain to explain is what the heck is the unlock of the crossing equation? Because the crossing equation was the most important point for the CFD problem. That was going to be the Poisson summation formula for the sphere packing. And then the other thing we're trying to explain is how do we deal with the fact that not all sphere packings are lattices. Okay. So maybe let's take a break now.
Maybe questions, I don't know.
Yes.
No questions?
Here is a stupid question. At which moment those points are spheres?
The only thing that characterizes them is the radius. If there are spheres, that means that we can reduce the problem to talking just about distances between the configuration of points. If they are not spheres, then you need to worry about the angles. And then the sphere is just characterized by where it's centered.
Wow. You were problems and you.
Typically spherical color, here cubical is the best.
But once you have optimal sphere package, you can always apply dilatation to go to ellipsoids. See, if you have optimal package of spheres, I just squeeze it in one direction. So if you give optimal package for spheres, I squeeze a little bit, so each sphere becomes ellipsoid. It will correspond to sort of optimal package in terms of those ellipsoids.
Twist the ellipses and maybe get something more optimal by not putting only the ellipses in the same direction. The ellipses have an axis, so maybe you could twist the axis and make them irregular in a way that makes something more compact, just having all of the axes aligned. By solving the sphere problem, you didn't solve the ellipses.
But you see, it's like no effect, or it's like maybe.
But it's clearly, it has not just, sphere, but just center. Ellipsoid has also the
No, I mean,
if you consider like RAM, so imagine that you generalize to spheres with multiple radii, so it's polystep, and you do the same for ellipses. And you just try to crank them so that maximize the density. Ellipses are much more dense than the random packing.
The optimal packing with ellipsoids, they are not all pointing in the same direction. So you cannot go back to the case with the sphere. Yeah, I guess that's what. I mean, maybe when the eccentricity is very small. Yeah. So yeah, to make the mapping to the Bootstrap as far as possible, we need to answer these questions. So what is the crossing equation for sphere packings? And that's Poisson summation formula, which I'll get to right now. And then question 2, how do we remove the assumption that we are dealing with a lattice? This Poisson summation formula will directly apply only to lattices. So first, Poisson summation formula. Which I think deserves the name theorem. I don't know if it's due to Poisson. It certainly bears its name. So what is the Poisson summation formula? Well, it's telling us the following thing. If you take a lattice in d dimensions, then if you take some function, decay sufficiently fast in the dimensions, and you sum that function over a lattice, you get the same answer as summing the Fourier transform of the function over the dual lattice. So that'll be a lattice. So I'm just not gonna write a lattice, but just it's a lattice, and let f be a function of rapid decay. So the technical term that's most suitable for this formulation is Schwartz function. So these are functions which have all derivatives, and all of their derivatives decay faster than any inverse powers of radius. So they decay all derivatives decay very, very fast at infinity. And let me denote f hat to be the Fourier transform. Let's say f to be a Fourier transform of f. So the Fourier transform, I'm going to use the following convention. It's e to the minus 2 pi I x dot y f of x dx. And the reason why Schwartz is nice is because the Fourier transform is an automorphism of the Schwartz space. So if f is Schwartz, then f hat is also Schwartz, and I guess vice versa. So f hat is also Schwartz. Now, what does the theorem say? Well, it says that if you sum f over lambda, so you sum the values of f over the points in the lattice, then you get the same thing as summing f hat over lambda star. Lambda star, remember, is the dual lattice. And the proof is actually quite nice and simple. It uses Fourier series. Let's prove it. So because little f is Schwartz, you can find its periodic sum. So you can find a periodization of f by summing over all points in the lattice, right? So now this, okay, first of all, this certainly converges because f is Schwartz, and f is periodic, meaning that if you shift x by any lattice vector, you get f capital F back. So because f is periodic, you can decompose it using the Fourier series, and like we said, the basis for Fourier series are plane waves whose momenta are in the dual lattice. So that's why the dual lattice appears. So write a Fourier series, which is a sum over the momenta in the dual lattice with some coefficients to be determined momentarily times the plane wave with momentum in the dual lattice. Okay, so how do we determine alpha? Well, we use the fact that the plane waves are orthogonal to each other in the unit cell. So if you integrate the plane wave with moment, so imagine y is in dual lattice. Integrate this plane wave on the unit cell. Well, you get 0 unless y is a 0 vector. So this is the discrete Kronecker delta times the volume of the unit cell. Right? If y is 0, then you get just the volume, the Lebesgue volume of the unit cell. So you get the formula for alpha, which is 1 over RD over lambda times the Fourier transform of f evaluated. And so you take this equation, you multiply by e to the minus 2 pi I xy, you integrate, use the definition of f. That's how this integral over the unit cell becomes that integral over all of RD, and that's how you get.
But integrating RD over lambda, what is actually?
Well, this is a periodic function, so it's a function of x because y is in the dual lattice. So this is periodic with period lambda. So this integral is well defined.
Sorry. First of all, you have set of points. You have discrete set of points at x. Why should I
X?
No,
X is not in the lattice.
okay. X
is in here. X is a point in RD. Y is in the dual lattice. I mean, this is periodic. This period is the lambda. So this integral is well defined.
So you integrate on some other domain.
Yeah. And you get this. So that's the end of the proof, but it really gives you kind of a nice generalization. So the top equation is x lambda f of x, and maybe let me do it x prime, x plus x prime. And this from here now, so alpha is that. It's 1 over d over lambda, volume sum over the dual lattice. So this is the Fourier decomposition of f hat y, but we get this extra from the exponential. So if you want to get the original theorem, you just set x to 0, special case, and this is just a statement that the shift, Fourier transform of the shift is the original function times the exponential. So that's not more than that. Okay, that's the Poisson summation formula. It's fine. Now using the Poisson summation formula, you can make the connection between even several lattices and modular forms that I was alluding to before. And so, as an example of Poisson summation formula, let's use the following f. So our f is only going to depend on the norm squared of x, so the radius of x. And we will choose it to be this function. Well, it's really a class of functions parameterized by tau. And so if tau is within the upper half plane, so t1, t2 are real, and t2 is positive, then so if tau is in the upper half plane, then this is a Schwartz function because it decays very, very fast as x decays fast with an e to the minus x. It's very fast. And the Fourier transform of f is the following thing. So it's minus I tau to the power minus d over 2. You can check quickly for yourself. Times minus I pi over tau x squared. So basically y squared. Right, so this function of x for parameter tau, if you Fourier transform, you basically get back the same function, but where tau is sent to minus 1 over tau. There's the nice property of it's called a Gaussian, this function, x squared. So that, by the way, means that the theta function of the lattice, the Poisson summation formula. Let's apply Poisson summation formula to this function. Well, the left-hand side of Poisson summation formula becomes the theta function of the lattice lambda, and the right-hand side becomes the distance. There is the prefactor, which is just a constant, divided by the volume of the unit cell, which appears in the Poisson summation formula, times the theta function of the dual lattice, evaluated at minus 1 over tau. Yeah, so this is now the Poisson summation formula of the function. And well, if you have a which is self-dual, then this is 1 because volume is 1. Lambda is the same thing. So you get a modular form. Kind of modular forms really only exist when this power is a multiple of 4. So that's why D should be a multiple of 8 for even self-dual lattices. So the even, maybe I should say so, even implies that theta tau plus 1 theta of tau, and so dual implies that the theta of tau is minus I tau minus d over 2 theta lambda minus 1 over tau. Yeah, so here modular formula tells you that these should be a multiple of. Okay, well, this function is the crossing equation, the analog of the crossing equation for lattices, because the left-hand side is some infinite sum over the lattice vectors of, now, this plays the role of the conformal block, where tau plays the role of z, so there's a relation between tau and z. It's an equation which holds for any value of tau, just like the equation holds for any value of z. So the spectrum of x squared kind of maps to deltas, more or less. And this just tells you that the sum over conformal blocks is equal to the sum of cross-channel conformal blocks, where now the cross-channel, instead of equals to 1 minus z, you have tau goes to minus 1 over tau. But I'll make this much more precise soon. But okay, that's the idea. This is the analog of the crossing equation for lattices. Is the analog clear? Why this is like the crossing equation? Both sides are some infinite sum. So this resolves the first question: what is the crossing equation for a lattice? I should say one more thing. Now you can this set of functions, as you vary tau, you get different constraints on the set of lattice vectors, and in some sense, it's a complete set of constraints that you can. In a Poisson summation formula, you have some general Schwartz function, and the claim is that you can get any Schwartz function, you can approximate any Schwartz function arbitrarily well by applying functionals to this equation, functionals in tau, right? So for example, you can set tau equal to I, and your function would be e to the minus pi x squared. You can take a derivative. You take a derivative of the equation with respect to tau equal I, you get something like x squared e to the minus pi x squared and so on, right? So by taking derivatives of this equation at tau equals I of any order, you can generate kind of any polynomial in x squared times e to the minus pi x squared, and this is clearly a basis for the space of radial for functions which depend only on x squared. Should I?
You have to find two latest on the right hand side.
From indeed, yeah, so this is an important difference between the equation that I have and this problem, is that the vector on the two sides are not necessarily the same, but the equation is still very constraining. But what I just wanted to say is that you can, by taking derivatives of this equation at tau equal I, you can generate more and more instances with the Poisson summation formula, where you get basically a complete set of functions that you can feed into the Poisson summation formula, because the functions that you get are essentially x squared to some power n minus pi x squared for any power of n. If you include arbitrary high powers of n, this gives you a basis for the space of radial functions in Rd. Just already you can see that the functionals will map to these test functions f to be used in Poisson summation formula. Well.
Go fast.
Yeah, it's even that's right. But it's enough. So indeed, so really the most general function that you could use is like any function for which the Poisson summation formula holds for any lambda. In particular, any Schwartz will do. The question is whether this gives you a sufficiently large basis. Well, it turns out that the optimal choice of f is an infinite linear combination of these derivatives. Maybe it will become more clear. So if you want to implement this kind of numerically, you would want to work in these bases, which are just the same as the conformal bootstrap basis derivatives at the crossing symmetric point. But let's get to the second question. So general sphere packing is not a lattice packing. So how can we apply this idea to general packing? So the idea is that you can approximate any packing arbitrarily well for the purpose of density by a periodic packing. Right? You can imagine you have some very random configuration. So now I'm just drawing the configuration of centers, something completely random. And imagine this as the optimal density. So I can construct a sequence of periodic packings whose density gets arbitrarily close to the density of the random thing just by taking some box, some very large box, and periodically repeating it. So I take a very large box, and I define a new packing which just consists of whatever is inside, all the points which are inside the box, and periodically repeated by stacking the box. And by making the box larger and larger, the density of this new periodic packing will become closer and closer to the density of the origin packing. It's kind of crazy. It sounds like a completely stupid idea. You just do the most stupid thing. You take a large box, periodically repeat it. It's good, And now the beautiful thing about this Kononowski's linear program is that it will prove an upper bound on any periodic packing, and therefore on any packing. Right? So if you have some universal bound for a fixed d, which is true for any periodic packing, this argument shows that that bound is actually true for any packing, because any packing is arbitrarily close to the periodic bound. It sounds insane, but it's true.
Do you expect, let's say, just thinking about all possible packing, not periodic, but I think also you expected it will be unique. Is it clear or not?
Well, it's not clear. I mean, the point is, so in a case in 8 and 24 dimensions, the optimal packing is actual lattice packing. So somehow this method is really only can be optimally good when the actual packing is pretty periodic, but it doesn't matter because it gives a correct upper bound. So that's all we want. We just want a method which gives an universal upper bound, and that's what this method does. So anyway, just to summarize, what I just said is that if you have a method that has an proven upper bound on any periodic pack, on the density of any periodic packing, then this upper bound is also an upper bound on density of any packing, because if it doesn't depend on a period, also on the number of vectors per unit cell. What happens here is that as you make the box larger and larger, the number of vectors per unit cell becomes very large. So your upper bound better not depend in a dramatic way on the number of vectors in the unit cell, and that's indeed the case. Okay, so how do we get this upper bound? So suppose you have a periodic packing where the spheres are at locations, sphere centers, at points which are of the form x plus, maybe I should say ai, where x ranges over lattice lambda, and ai are some vectors in Rd, and I runs over some finite set from 1 to n. So this is a packing with period lambda with n vectors per unit cell. Then we can write down the Poisson summation version of the Poisson summation formula, which still looks like a crossing equation for this situation. So what are we going to do? We are going to sum. Yes, sorry. So take Schwartz function f. Going back to the first case, f is a Schwartz function thing, or any function for which the Poisson summation formula holds. And then consider this sum. We're just going to sum f, not just over the lattice, but the natural generalization is to sum it over all the distances between spheres. So x plus ai minus aj. Right, so the set of possible x plus ai minus aj are precisely the set of vectors which separate different sphere centers from each other. Okay. And what does the Poisson summation formula tell us? Well, just apply it. It's going to repeat this, and now we have the 1 over volume of the unit cell, sum over the dual lattice. Then there is this exponential factor. So this is the shifted version of the Poisson summation formula that we had in the proof. Y equals ai. So y of ai minus aj. So this I is just the imaginary radius of the index times the f at y. Now, why is this nice? It's nice because if you do this, if you put it on inside, this thing becomes a perfect square. So I'm going to put the volume of the unit cell outside. The sum over the dual lattice outside. And now I'm going to do this sum here becomes a modulus square of something. So that's really the key idea. F hat. So now it's nice because we are preserving positivity. We are summing f with some positive coefficients, which is just 1. And now we are summing f hat with some positive coefficients, which is this positive thing. Okay, so this is like a version of the Poisson summation formula, which is useful for a periodic packing.
The method of this
Yeah, this is the
point of
this is the method of Conan. I'll write it now. This is just like this is the starting point. So theorem of Conan Otis, which uses this identity. This is I think from around 2001. So suppose you have a word function such that the following conditions are true. First of all, there's some normalization, which is not so important. Secondly, let's suppose that f is non-positive whenever for all sufficiently big vectors, so for all vectors that are whose length is at least r. And finally, suppose that f of hat is non-negative everywhere. So if such a function exists for this value of r, then any sphere packing in d dimensions satisfies an upper bound on its density. So of the packing is upper bounded by the volume of the ball, d-dimensional ball, whose radius is r over 2.
Is f the function from the whole RD, or is it RD over lambda?
Oh, there is no lambda here. Lambda doesn't. You're not fixing any lattice here.
The information about f does not enter the outcome of this bound.
Yeah, the information is r. So okay, let me rephrase. So you're trying to construct some auxiliary function f, which has some properties, and these properties are in some tension with each other. But let's discuss them a little bit. So first, the Fourier transform of f is non-negative. This is consistent with f0 being 1 because this is the integral of Fourier transform over all of RD, so this is fine. But it's in tension with this condition. But you cannot have a function which is negative everywhere whose Fourier transform is positive everywhere. That's not possible. But you can try to make a function whose Fourier transform is positive everywhere, which is negative as much as in as large a region as possible. But you're not going to be able to make this region arbitrarily large, right? So the function is non-positive for everywhere above radii r, but r cannot be made too small, because if r is made too small, these conditions are just too much in tension with each other. Nevertheless, if you can find such a function for some r, then Kononelkis proved that for that r, you compute this number, which is the volume of the ball of radius r over 2, the dimensions, and this gives you upper bound on density of all packings, whether they are lattice, periodic, non-periodic, just any packing. And the proof just uses this identity. So let me repeat this identity here. So first, so imagine you have a packing, and without also generality, it can be periodic. It's a packing, this packing, with sphere centers at these locations, or this lambda, these values of vectors. So let's prove that for this packing, you get an upper bound on the density. And well, the density of the packing doesn't depend on rescaling of all the radii, but basically just applying some scaling. So regardless of generality, we can assume that the shortest distance between sphere centers is exactly r. So imagine we have this function f. Imagine we have a sphere packing, and let's rescale the sphere packing such that this shortest distance between sphere centers is r. And let's now look at the Poisson summation formula for that value of f. Well, almost all the terms on the left-hand side will be negative, will be non-positive, right? Because we know f is non-positive as long as x is greater than r. So the only terms on the left-hand side which have a chance to be positive are those when x is, well, basically when this is a zero vector, because these are the vectors between spheres, the connect spheres, and we just said that all of the spheres have distance between centers at least r, so that's where the function is non-positive. So the only chance that this thing is positive is when this is 0, which is when x is 0 and I is equal to j. Okay, so if we, let me just, so how do we, so proof of theorem Kononelkis. Proof of Kononelkis. We take this identity and we write the term where this is 0, so that one appears n times because I is equal to j, but it can be anything from 1 to n. Right, so it's n times f0, and then everything else is negative on the left-hand side. So this one comes from I is equal to j, and x is equal to 0. And on the right-hand side, well, on the right-hand side, everything is non-negative because f hat is non-negative, and this is non-negative. But we are still going to isolate. Let's isolate a term where y is 0. When y is 0, this is 0. So this is n squared. So you get 1 over the volume of the unit cell times n squared. from here times f of hat at 0 plus something positive. So this is something positive and this is something positive, which means well, let's cancel n from both sides. N is positive, so nothing bad happens. But you get that n over rd over lambda is less than or equal to. So we put all the pluses on the left-hand side, which means that all of this shifts the first term more negative. No, that's just I put this to the left, so that's why I have less than or equal to, and I have n over r to d. I divide both sides by f hat of 0, which is the normalization is 1, so I may as well just 1. And I could say with more polynomial. Oh, clearly, you can just multiply f by some constant, and this will, doesn't change anything. You can also rescale. You can also do some rescaling of x, but this will also kind of transform cover n. You can just assume this condition. Okay, so what does this mean? Well, remember that the density. I'm going to continue to prove here. Remember the density of a sphere packing is the number of vectors per unit cell divided by the volume times the volume of the ball in d dimensions of radius, which is 1/2 of the distance between spheres. But then we know this is at most 1, so this is at most volume of the ball. Oh, okay, it's actually already there.
Here, what picture created so this one which appears on the right hand side of the ball to block. All from the relation that have to left to 1. But what will happen if I had a number? You could put the numbers in. For instance, so this one which appears here was actually so imagine that I could put f of 0 to any number just special normalization.
Let's keep this as it is. Let's not fix it. And let's plug it in here. So what we proved that. So now we are not assuming condition 1. So rho is at most f equals 0 over f hat 0 of the volume of the ball r over 2 over d. Okay, but now this formula has some gauge symmetry. First of all, it has a symmetry of multiplying f by constant, because this ratio is fixed, but it also has a symmetry of rescaling space by a factor. So if you suppose you have some f of x and you define new f, a twiddle, which is, let's call it g of lambda, which is f of lambda x, then f hat, then g hat is the same thing as f of x over lambda to the d. But also your r is going to change. R is going to, your new r is going to be r over lambda to the d. So the lambda gets cancelled. R volume of unit ball gets a factor of lambda to the d. This gets a factor of lambda to the d. So you may as well just assume that the two constraints from the gauge symmetry.
What I'm saying, but it's this symmetry is the key ratio fixed. The ratio doesn't not the variant that is those two symmetry to match. But why should one?
You can choose any ratio that you want. Then the theorem is going to have this.
Yeah. Because this very good.
But the upper bound on row, doesn't depend on what you choose. You can write a more general theorem, which is actually more general, where you set f0 to be a, f0 to be b.
Yes,
then you're going to have a over b here, but the bound that you get is the same as if you assume it's the a and b are 1 because of the equation. Because if you change a and b, the optimal R is going to change by the rescaling procedure. So this thing will cancel that.
There can be multiple F's with this property, right, at any given day. Is that true?
Yeah. I mean, what you want? Maybe what you want is F's with the best possible R. So the smallest R is the best, right? Because it gives you the best upper bound. Maybe there are some have multiple even at the best R. Like an R. Okay, so now to prove optimality, to prove that E8 and H are optimal, optimality of E8 and each, you just need to find the right F in 8 and 24 dimensions. I mean, the just is kind of an important just. Find what do we need to know, or what we need to find F and satisfying 1, 2, 3. And in B equal to 8, we should have that R for this probability of R, which is square root of 2. And for D equal to 24, we should do it for R2. So do you agree that if we can find F satisfying 1, 2, and 3 for these values of R, then we win? That's like what I did before I did. And well, this extramality gives you a lot of information about F and F hat. And that's because for the bounds to be saturated, all of the terms that we threw away need to be 0. Like we had the positive summation formula, then we threw away many terms, like all of the non-identity terms on the left and all of the non-identity terms on the right. The only way the bound can be saturated is that all these terms are actually 0. So that means that this is what F looks like. So let's say we are in 8 dimensions, and let's plot F of R of x as a function of x squared. So it needs to be non-positive here, everywhere above 2, but it needs to vanish at 4, 8, and so on. So it needs to have double zeros, or even order zeros at these locations. Then it becomes 1 for F hat. It's a little simpler. F hat needs to vanish 2, 4, 6, 8, but it's non-negative everywhere, so it just has double zeros straight away. The function looks like in D equal 8. And for D equal to 24, is exactly the same picture, except now the first 0 is at 4. So the simple 0 is at 4, and here the first double 0 is at 4. I'm not going to draw that, but I'm just going to focus on the 8-dimensional case from now on, just for simplicity. But they go the same story.
The notice is still the approach of the method.
Yeah. My approach is the same, basically the same as the approach of mathematicians, just that we realize that they're the same a bit later. So this is the approach. Well, this is the approach of mathematicians to the sphere packing problem, which is the same as my approach to the CFT. But it was only later realized that actually the CFT and sphere packing can be mapped to each other. Well, what I'm explaining so far in the lecture is the approach of mathematicians. So you have this function, which needs to have the structure of zeros, And it turns out there is a unique function, unique under the assumption that it only depends on the radius squared, with the structure of zeros. So you can kind of, you can forget all its positivity and just impose a structure of zeros, and you will find a unique answer, which is what I'd like to explain. So it's useful to split the problem into the Fourier odd and even part. So let's define G plus or minus to be the following Schwarz functions. So what do we need to do? We need to find f which looks like that and which satisfies. Then that proves that E is the best stacking in dimensions. So how do we construct it? Well, we construct independently the Fourier odd and even part. By we meaning Beazovska was with it in any dimension. Okay, so G has the nice property that G plus or minus is either plus or minus, so G hat plus or minus is either plus or minus G. And actually, I'm going to, plus or minus here. And actually, I'm going to just focus on G minus. It's even for mathematicians, it is kind of the core problem, and it's not very hard to modify the method to get G plus. Basically, the construction of G plus and G minus are really very similar to each other. So I'm just going to focus on the G minus, and maybe later I'm going to make some comments on how to get the G plus. So what G minus, what does it look like? Well, it's the bottom picture minus the top picture. So because we are subtracting f, there is a simple zero at 2 with positive slope, and then there are double zeros everywhere, and then it's 0 at the origin, because the f0 is equal to f hat 0. So this looks very much like the extremal function that we saw at the beginning of the lecture and during the last lecture. So the claim is that you can literally get this function from the same extremal functional that I found for CFTs, for delta phi equal to 1/2. So we need to construct G minus, and we are going to construct it G minus as an action of the omega that was at the beginning of the lecture for delta phi equal to 1/2 on something, on some function. So we just need to find that something. But we already kind of saw that because this something is just the Gaussians. The Gaussians appearing in a Poisson summation formula.
So how do you know that G minus isn't 0 between 0 and 2?
I think it's non-zero. You don't know. I mean, okay, it's not important for the. I mean, what needs to be true, I think, is that it needs to be positive. Yeah, I think it needs to be positive from here on, right? Because it's that minus that, so it's 0 here, positive or non-negative here, and it has zeros at all these places. Yeah, there's no constraint, but there's a unique function with those first properties. So. Okay, so let's consider slightly souped up Gaussian. Maybe let's call this. Yeah, let's define this block. To be just the Gaussian that we had before. I tau delta so that if we if you think of it as a function of x, if we plug in x squared for delta and think of it as a function on RD, then the Fourier transform with respect to x gives us what we saw before. It gives us the Gaussian with the same value of delta evaluated at -1 over tau. Sorry, x. I mean, maybe I should say y squared. Right, so I think of this, I take a Fourier transform with respect to x, the function of y, which means that you can get, so you can get Fourier odd for its functions by, before I say that, let me simplify it a little. There's a Dedekind eta function which satisfies that eta of tau is minus I tau minus 1/2. It does -1 over tau. It's a little bit more convenient to get rid of this factor by multiplying by the rate part of Dedekind eta. If you take Dedekind eta to minus b times this g x squared tau and Fourier transform, then as a function of y, you get the same thing with tau replaced by -1 over. That's just a trivial thing to do. You trade this d over 2 for the d star of the eta function, which means that if we write g minus of x as some linear functional, like a linear functional acting on functions of tau that act on this anti-symmetric combination, it's like the S channel minus D channel. Right, so this, for any linear functional, this is Fourier odd, because if I activate Fourier transform, linear, so it commutes with omega, it exchanges the first term with the second term. Yeah, so in SDFT, we had a function which acted on these crossing antisymmetric combinations of blocks. Here, we can replace it by saying that the function is Fourier odd, which is equivalent to the statement that it's a linear function acting on the linear combination, this anti-symmetric combination of these conformal blocks. Okay. But we still need to find omega, and the claim is that omega is basically, the big omega is basically the little omega from the previous lecture. But remember that little omega was acting on functions of z. So remember that little omega was acting on z to the minus delta 2 delta phi of this block dz. So it's structurally very similar, but there are some differences. So instead of tau, we have z, and when tau goes to -1 over tau, then z should go to 1 minus z. Right, so what we need to do is to find some transformation between tau and z. And that when z goes to 1 minus z, then tau goes to minus 1 over tau.
So, yeah, you know what is h.
I know what is h, yeah. But it's actually not so important what is h. Oh, but I mean, here you also know what is g. It's fine. It's very symmetrical. Are you saying?
G was negative.
Oh, it's some 2f1, but yeah, actually it could go. So what did we need to know about g to prove the previous theorem? All that we needed to know is that when you take z to z over z minus 1, then this transform is on phase, which is I pi or plus or minus, depending on whether you go above or below the branch cut, times. So if you remember the proof from the end of last lecture, this is really the only property of g that I used. And this property has a very analogous property here, which is that if you transform tau to tau plus 1, then you just get a phase. I should say, if we shift tau to tau plus 1, then you get I pi delta times h delta. Very simple. So okay, so now if we combine those, so okay, we need to map it. We need to write z as a function of tau. So we are looking for transformation lambda, such that lambda of minus 1 over tau is 1 minus lambda of tau, and lambda of tau plus 1 is lambda of tau over lambda of tau minus 1. So this guarantees that the two problems are mapped to each other perfectly. That's right.
So for the h functions, these two terms we should have inside this bracket, they are related by the Fourier transform.
Yes.
So function g conform block. So that's second order differential equation.
Yeah.
If I do Fourier transform on that second order differential equation, I have to reproduce equation which would correspond to second term, second line inside the bracket.
No, they're not. No. The analog of Fourier transform for the blocks is not the Fourier transform.
No, I'm not talking about Fourier transform. Basically, what you're saying, I want to be pragmatic. So I have differential equation for g. Now you think I'm going to change the variables. The condition for change the variables, that after I do change the variables, I will get some new equation, which I could formally should be able to identify with the equation for second term size of bracket.
Yes, but then what?
Because what I don't confused that for these two agents which were inside the first line, they were related to each other by the Fourier transformation.
Yeah.
The Fourier transformation was a crucial part of the whole construction. So now we come to second line, and these two G's, they come out from the CFT, one dimensional CFT. And they construct in different ways, like solution to so-called differential equation. So now I'm comparing this equation, I'm asking the question, what's the analog of Fourier transform? Let me ask the question, but let me ask the question now. Will you please shut up before
Well, so I'm getting rid of the Fourier transform. I'm trivializing Fourier transform by saying that instead it's a functional acting on this difference. It may look like a more complicated formulation, but it's equivalent, right? So instead of looking for a Fourier odd function, I'm looking for a functional that acts on this combination. And in this formulation, it's much closer to the original formulation for the CFT. It's a very good question. What is the analog of the Fourier transform for the conformal blocks? And it's probably some integral transform, which if you act on delta, so it's like it's an integral transform in a space of deltas, which if you apply, you get the conformal block at 1 minus z. I thought about it a little bit at some point, but I never really made it. It's a good question. So, but the problem is that the second order differential equation satisfied by g is rather different from the second order differential equation satisfied by g at 1 minus z. And indeed, there should be some integral transform which connects the two, but it's not essential. But it's a good question. I won't need to answer it to finish the proof. Okay, so we need this mapping between from tau to z such that when tau goes to -1 over tau, you get 1 minus lambda. And when tau goes to tau plus 1, then you get this. And there's a unique function which satisfies these properties. It's called the modular. So there's a unique lambda. It's called the modular lambda. It's a modular form. It's a modular function. Not for SL2Z, but for a degree 6 subgroup, which is called gamma 2. And it's degree 6 because the cross ratio is permitted by S3. These two things generate a group of order 6, which is this non-abelian group of order 6. So anyway, there's a unique function. You can write it explicitly. Lambda of tau is some ratio of theta function. It's the Jacobi theta to the 4, Jacobi theta 3 to the 4. Okay, so there's this function. So this is, we are almost there. There's just one small thing, which is how is B and delta phi related to each other. So the key to understand that is seeing how, what are we? We are trying to use the same function omega and act with it now on this. And we can already do that because Z and tau are connected to each other. But we need to make sure that what we are acting on behaves in the same way as the G was behaving before. So that's the key property, which was important in this note. This is how you get, this equation is how you get the cos squared. This is how you get the oscillation to double zeros. But this guy, you still need to deal with this guy. So Z goes to 0 with Z minus 1 is like tau going to tau plus 1. And under that, this one, eta function, just picks up a phase, right? Because eta, so what is eta? Eta of tau is q to the 1 over 24, 1 minus q, 1 minus q squared, and so on. So eta to the b, tau plus 1, is, it just comes from this, because all of these guys are invariant, so it's 1 over 24, it's e to the I pi b over 12. Remember that q is e to the 2 pi I tau. So when you shift eta to the d by 1, you get it back with a phase. Okay. But this one doesn't transform so nicely under z goes to z minus 1. We need to massage it a little bit. Right, because if you shift it, then you get some extra factor 1 minus z, which is not very nice. But you can multiply it by some symmetry. You can always multiply this combination by something which is symmetric under z goes to 1 minus z. It doesn't spoil anything as long as you divide before acting with omega. So now let's choose omega such that this function is an eigenfunction of z goes to 0 over z minus 1. Right? Because eta was an eigenfunction with this eigenvalue. So let's find alpha such that it's an eigenfunction. And it turns out that it's, alpha needs to be 2 delta phi. I mean, we can just do it. So let's just, if you send, so under z goes 0 to z minus 1, you get, maybe the right way to say it is that let's take z negative above the branch cup. Then you get e to the I pi alpha minus 2 delta phi. to the power minus z alpha minus 2 delta phi, 1 minus z to the alpha, and this should be this, and this should be the same thing as I pi alpha minus 2 delta phi as the original thing evaluated at z over t minus 1, which is whatever you get. Maybe I don't want to waste too much time, but basically by these constraints you get that alpha is 2 delta phi over 3. Yeah, I guess I only have 5 minutes. But let's just, it's a simple calculation. You just plug in 0 over t minus 1 and you get alpha is that. So now this phase should be this phase for the value of alpha. So d over 12, which is this phase, oh sorry, it's eta to the minus d. So it's this phase with minus must be alpha minus 2 delta phi, which is 2 delta phi over 3 minus 2 delta phi, which is 2 minus 6 is minus 4 delta phi over 3. So d minus d over 12 is minus 4 delta phi over 3. In other words, d is 16 delta phi. Okay, so what? Yeah, just to summarize, you get how do you constrain g minus x? You take omega, multiply. Maybe I can write. Yeah, so this Fourier odd part of this extremal function for a-dimensional sphere packing, you can get it by taking the extremal function from my previous lecture that I constructed for CFTs and act with it on this correction factor e to the 1 minus z to the power minus d over 20. Let me actually put the delta phi here, so that's d over 16. Delta phi d over 16. Then here's minus d over 24, which is the correction factor that we found. And acting on the Gaussian h in d dimensions, now we need to pull back using the lambda, so going back between z and tau. Yeah, so essentially because the only thing that we needed for the proof in the previous lecture was the transformation of h g under that shift, and the antisymmetry is implemented by lambda, guaranteed that g minus will have the right structure of double zeros. Then when we discover this connection, you can just take function for 1D CFTs, do this math, you look at Vyazovska's paper, and you see the same thing. And also, okay, also so this for d equals a, and for d equals 24, you apply the same formula. And so the nice thing about this transformation is that in the mathematicians papers they are dealing with functions of tau, so they're all modular forms. But under this, essentially, the only modular form that you need to know is this lambda of tau, because once you use that lambda of tau to make the modular forms into the nice rational functions that I wrote down on the boards. So in the context of CFTs, the proof is much simpler because you're just dealing with rational functions instead of modular forms. Something that I didn't discuss is the construction of G plus. But the G plus is something similar where you just replace minus with a plus. And you need to work a bit harder to find the corresponding functional, but that's kind of big. In the case of CFT, it's like dealing with the crossing equation with the wrong sign. Like looking for in which solving crossing equation where sum over blocks minus sum over blocks in a D channel. But it's also interesting. It has been constructed. That in principle completes this.
Before, but she gets the formula.
Yeah,
She also gets.
that's right. Yeah, she had a very smart ansatz. So basically, but ultimately, the formula is is the same. It's the same thing. Some contour integral. Contour integral in the z variables. She had a contour integral in the tau variable, which is some kind of a Laplace transform. Because what you're integrating against are these Gaussians. You just need to find what are you Laplace transforming, and that's specific modular form in her case, or in my case, it's a specific rational function that are mapped to each other by the modular lambda. Just a few concluding words. So I guess we saw in these lectures how to constrain various geometric objects using some kind of more or less algebraic axioms. And I think interesting open direction is that for CFTs, we really don't have this corresponding geometric picture. We only know the axioms. So for example, the 3D Ising model more or less defines the solution of these algebraic axioms. It would be very, very nice to, if there was actually something like a geometric construction. So for sphere packing, there is this very mysterious object, which is E and the Leech lattice, but it's actually not so mysterious anymore because you can construct, and it happens to saturate the bounds. Whereas for the 3D Ising model, we know it saturates some bounds, but we don't have any explicit construction like we have for the E8 and Leech. Be nice, something like that exists also for things like interacting CFTs. Okay, that's it. Thanks.
Do you have questions?
Yeah, Paul, a bit of a technical question. I missed the part where how did you relate alpha to delta phi? Just
Yeah, I can just write it. Yeah, so we have this vector, which transforms like that. And now you have this vector, which you need to make sure that it transforms in the right way. So you put z over z from alpha. And okay, so that's e to the I pi alpha. So I'm taking z negative, right? So z is now on top of this branch cut, 0. So I get minus z alpha minus 2 delta phi, 1 minus z to the power alpha. So that's just the same function at the branch cut. And now I evaluate the function at z over z minus 1 instead. Plus alpha, and this turns out to be equal to minus z. So now I send z to z over z minus 1. Turns out it just flips alpha. So that's equal to alpha minus 2 delta phi, 1 minus z to the minus 2 alpha plus 2 delta phi. Okay, now if I set this function equal to, there's basically this power needs to be that power. So
yeah.
alpha is 2 delta phi over 3.
What was the motivation for the crossing this wrong side? So to construct us from the CFT side, there so that crossing is the wrong side.
Crossing with the wrong side. Well, for me, my first motivation came from trying to understand the sphere packing better, because in sphere packing there is both sides are important. But I think it's also important when you do global symmetries. So when you have like bootstrapping something with one symmetry, then there are various channels, and in some channels you get the usual crossing equation. Well, basically, if you have the usual crossing equation where the two sides don't have the same spectrum, you can just symmetrize and anti-symmetrize under z goes to 1 minus z, and then you're naturally led to studying this wrong sign crossing.
Just to understand the way things are happening, there was a delay between their solutions and you had calculated this bootstrap.
Yes.
And realized that they were the same.
Yes, so the history is the following. So Wiazowska wrote her paper in March 2016. Then a week later, the 24-dimensional one. I wasn't aware of it. I wrote my paper also in 2016 in the end of November. But if you look at the papers, they are just completely. It doesn't look very much the same. Then I went to Stony Brook for my postdoc, where we noticed that the two things look kind of similar. It took us 2 years to find the connection that I explained today. Oh, you may parallel quickly. Yeah. Then there are various other developments. The mathematicians did this universal optimality story with kind of basic interpolating functions. That's something that we found before them. So there were some things that the mathematicians did before us, some things that we did before them, and we eventually found a connection between the two sides.
Yeah, but when you wrote the paper, it was not about.
Well, so the first paper has nothing to do with sphere packing. I knew nothing about sphere packing. It was about 1D CFTs, and then that was in 2016, and then 2019. Maybe I should I can give the references. In 2019, we wrote a paper where we explained what the connection is. Where we explain how to map Wiazowska to my proof. Or vice versa. So the chronology is so Wiazowska is this one. And I really recommend reading it because it's very nicely written and it will give you another perspective on these lectures. Then Wiazowska and friends. So this is 8 and this is 24 dimensions. I don't know if the ratio of number of authors is the same as the ratio of dimensions. But almost the same. So there's 0, 6, 5, 1, 8. So this is 24 dimensions. Then my paper, which has nothing to do with sphere packing, but it proves this theorem for CFTs, is 1, 6, 1, 1. Okay, and then the connection. Okay, so this is sphere packing. This is 1D CFT. And the connection between the two, which is what I explained today, is with Hartmann and Rastelli, which is 1905, 110119. Okay, I also recommend very nice review of Wiazowska's solution by Henry Kohn. So this is maybe the most readable account of the sphere packing business that there is. 1, 6, 1.